Hello everyone, welcome back to our searching and sorting algorithm series. Today would be part 7 of the series and we will dive into the quicksort algorithm. What is quicksort? Quicksort is an efficient sorting algorithm that follows the divide and conquer technique. It is widely used because of its speed and simplicity. First, quicksort selects a special element called the pivot. By default, the pivot is often the last element in the range being sorted, but it can also be the first or middle element depending on the implementation. Next, the array will be divided into two sections, the left portion and the right portion. For the left portion, it contains elements less than or equal to the pivot, and as for the right portion, it contains elements which are greater than the pivot. But here's the interesting part. Initially, the left portion would be unsorted, and the right portion is already sorted relative to the pivot. To accomplish such thing, we need a helper method. Quicksort applies this partitioning logic recursively to the left and right portions until the entire array is fully sorted. This systematic division and rearrangement are what make quicksort so powerful. Okay, now let's look at the code for our quicksort. There will be two sections of code breakdown. This section will focus on the partition method, which is the helper method that will be used recursively in the main sorting method. So first we have our pivot. In this implementation, we will set the pivot as the last element of the current portion. Here we say that our index I is behind the index j by default. To do this, we assign I as the following value, left -1. So if you're wondering how it works, we use I to track the position where the next smaller element than the pivot should go. Initially, I will start before the beginning of the array being sorted, meaning I equals -1. Since arrays start with the index 0, I will be -1. On the other hand, j scans through the array from the start of the segment to just before the pivot. It checks each element to see if it's smaller than or equal to the pivot. And moving further on, we will discuss why I lag behind j and how we perform the swapping of elements between the elements at I and elements at the index j. So here we can see a for loop that checks for certain conditions to perform a swap between the two elements that I've just said. So looking at the for loop conditions, we can see that our index j will start from our left index, which is typically the start index of our sorting portion or our sorting range. So left would be the starting point and right would be our ending point of this current sorting section. So during that section, during that portion or partition, whatever you may call it, we will check for certain conditions. If it matches the conditions, we will perform a swap. And to perform a swap, we would have to increase the index I. Because we assigned -1 to I. So we can't just swap elements at the index -1 because it doesn't exist. We must increment I before doing any swapping. So I will be incremented, and therefore the swapping process comes in using a temporary variable. And it's pretty straightforward. Let's move on. Here, after the loop ended, we will place the pivot at its correct place. So here we also increment I, because if there is no swapping above, we would still be stuck with I being -1. So to handle that edge case, we have to increment I and then perform the swap, placing the pivot at its correct place. So this would be our partition method or our helper function, and next we will move on to our main sorting method. As you can see, here we have the sort method, and it doesn't really do much except checking the right conditions to perform recursive calls to the partitioning method. As you can see, we have the parameters left, array, and right. Left would be, of course, the starting point of our sorting section. Right would be the ending point of our sorting section. And the array will be the array that we are sorting. Here's the base case. Since this is a recursive algorithm, we need to create a base case, unless our call stack would face a call stack overflow error. Stack overflow error. So here will be the base case, and it checks whether left is less than right. So if left is less than right, it means it's okay to further on call more recursive functions on these certain sorting sections. So if our left or starting point is less than right, it will be impossible to perform the partition method, since it doesn't really make sense. So left must be always less than right. In other words, we can say that our starting point must always be less than our ending point. Okay, let's move on. Here we have the integer index of our pivot's location, and we obtain it by performing the partition method, and it will return the index of the newly placed pivot, as we have looked at our code breakdown of the partition method. From the partition method, we will get the index of our new pivot. Our newly placed pivot. Next, here we have the recursive calls to sort these sections that we input. So for the first recursive call, we have the left, we have the parameters consisting of left, array, and pivot -1. So we will explain what these are saying down here. So basically, this part means that we are going to perform the partition method upon the left side portion of the pivot. Okay, left will be our starting point of our sorting section, and pivot -1 will be the index just before pivot, meaning that we are going to perform partition upon that sorting section, upon that range. For the another recursive call, we can see some values have been changed, of course. Since we're calling upon the right side of the pivot, or right side portion of the pivot, we have to change the starting point of our sorting range. We change it as pivot +1, meaning that it will start just after pivot. Okay, pivot will be the index of the pivot, and we add 1 to it, meaning that we will start just after pivot. And our ending point would be simply right, of course, since it is going to be the right half. Okay, let's move on. Here we can see a visualization example. We have an unsorted array or list with various numbers, and we will perform our quicksort algorithm manually. So we set our indexes and our pointers. For now, pivot will be at 16, and just as I've said, I will be -1. So it's not really in the range of the array yet. J will start from 0. As you can see, we are going to linearly check if element at J or index J is less than or equal to the pivot. Okay, let's start the loop using the index J. So first we check if 12 is less than or equal to 16, which will turn out to be true. I get incremented to prepare for the swapping process. I get incremented to 0. We perform a swap between these two indexes, and it will stay the same because they are pointing at the same element or the same index. Nothing will change for now. J gets incremented. We compare 21 to 16. Does nothing because it doesn't check our conditions. J gets incremented. I will still stay at its position, which is 0. Okay, we check 15 against 16. 15 is less than 16. We perform another swap. And remember, to perform another swap, we always increment I first. We increment I first. We will use temporary variable, and we will swap between elements from I and J. In this case, we are swapping 15 and 21. Here, we swap these two elements. J gets incremented 32 against 16. Nothing. We will do nothing. Now it's 10 against 16. 10 is less than 16. We will perform another swap. I gets incremented. Two elements get swapped. 10, 21. J will get incremented as well. Here, pivot and J are pointing at the same index, meaning that the element at J is equal to the element at pivot. Therefore, it checks our conditions to swap. I will be incremented. A swap will take place. There we go. We have reached the end. Okay, so our previous call, recursive call, has finished. Here will be another recursive call to the left portion. Under here we can see the exact call which causes this process. Okay, let's start the process manually again. Here we set our indexes and our pointers, because as you can see, we set the range from 0 to 2, the index 0 to the index 2. So previously obtained pivot was 16, right? So the index of our previous pivot was 3. To call the left portion, we decrement our previously obtained pivot's index. So we get 2. So it starts from 0 to 2. Okay, I will be -1. We check the conditions. 12 is greater than 10. We will do nothing. J gets incremented. Still, no swap is necessary. Here, pivot, the elements at pivot and J are the same. We will perform a swap. There we go. 10 goes to the index 0. 12 will be at the index 2. Okay. Here, at this point, we will call the recursive function. We will recursively call the partition function to the left portion but the call will be removed from the call stack because the condition saying that left must be less than right doesn't really check. So that call will be removed from the call stack. Therefore, we will perform the partition method upon the right portion of our pivot. Here will be the right portion. It starts just after our previously obtained pivot to the right index, which is 2 in this case. Okay, so we are recursively calling the portion starting from the index 1 to 2. I will be at 0. Okay, this time I is not at -1 because we inputted the starting point of our sorting section as 1. As we decrement 1, we get 0. So I will be at 0. Okay, so we check 12 against 15. We will do nothing because 15 is greater than 12. J gets incremented and now pivot and J are pointing at the same element. Therefore, we will have to perform another swap. To perform a swap, I gets incremented, okay, and there we go. We swapped between two numbers. Now we have 10, 12, and 15. Moving on, we will perform another recursive call to the right portion. Okay? So going back like 2 recursive calls, we had 16 as our previously obtained pivot. So to the recursive call to the right portion of 16, we are starting from the index of 4 to 5. So we will perform partition methods on the range of index 4 to 5. Okay, I will be less than J, of course. J at pivot compared. J is less than pivot, so we'll perform a swap, which will do nothing because J and I are pointing at the same index. Okay, J gets incremented, and since J and pivot are pointing at the same index, we will have to perform another swap. So here we will have to perform another swap, but as we increment I, we can see that both I and J are also pointing at the same index. Therefore, there will be no change. And if you look at our array now, we can see that it has already been sorted and our process has reached to the end. And before talking about time complexity, I will briefly explain why I is less than J and why I lag behind J. I only moves forward when J finds an element smaller than or equal to the pivot. This ensures that all elements before I are less than or equal to the pivot, and everything after I but before J is greater than the pivot. When J finishes scanning the array, we will swap the pivot with the element I plus 1. This step will place the pivot in its correct sorted position in the array, just like how 16 got its place in our first recursive call or our first function call, and how other elements follow to do the same thing. Okay, now we have reached time complexity. So when analyzing quicksort, it is important to consider how pivot selection affects its performance. In the best case and average case scenarios, the pivot divides the array into 2 roughly equal halves at every step. This keeps the recursion tree balanced, and the time complexity becomes O of n log n. However, in the worst case scenario, when the array is sorted in reverse order or if the pivot is poorly chosen, the algorithm becomes inefficient. The recursive tree becomes unbalanced, leading to a time complexity of O of n squared. But don't worry, quicksort efficiency can be greatly improved with optimized pivot selection methods. Techniques like the randomized pivoting or median of 3 can ensure more balanced partitions, minimizing the risk of encountering the worst case. Now let's talk about the space complexity of quicksort. Quicksort is often praised for its efficiency, but its recursive design does have a cost. It creates stack frames as it dives deeper into recursion. In the best and average cases, the recursion depth is proportional to log n, resulting in a space complexity of O of log n. However, in the worst case, when the recursion is highly unbalanced, the depth can go up to n, making the space complexity O of n. In addition to recursion, quicksort also uses a few variables during its process. So, here are the variables used. Array, which is of course the array that we're sorting. Pivot, I skipped over a variable. So pivot, the value around which partitioning occurs. I and j, indices used to manage and track partitions. And temp, a temporary variable for swapping. These variables contribute a small constant amount of additional memory overhead, but of course recursive call stacks kind of ruins its constant space design. Okay, now let's write the code for our quicksort algorithm. First we will start with the main method. So it will be sort. We need these parameters. Left will be our starting point of the sorting section, and our array, and right will be the ending point of our current sorting section. Here will be the base case. If left is less than right, we will only perform the recursive calls if left is less than right. Otherwise, we will remove it from the call stack. So if left is less than right, first we will need the pivot. Okay, wait, we will have to create our partition method. Left, array, and right. Okay, it will return the index of our newly placed pivot. So we will obtain the index of our pivot by using this method, our helper method. Left, it will be left, array, right, they're all the same. And then we will perform recursive calls to the left portion of the pivot and the right portion of the pivot, starting with the left portion of the pivot. So for the left portion of the pivot, we'll start from left. Same array, we will have to change the ending point of our sorting section. So it is going to be the left portion, so it will end at the index just before our pivot. For the right portion, we will have to change the starting point. It will start just after our pivot. And the same array till the end, which will be right. Okay, now our sort method is done. Let's write the partition method. First, we will have to obtain the pivot which will be at the end of our current sorting section. We can change to optimize our code. We can change our pivot setting configurations. Some people will use the first element as pivot or the middle element as pivot, and there is a technique that uses pivot selection randomly. For now, we will just stick to picking the last element as pivot. Next, we will have to set I as the element, as the index just before j -1. So left will be our starting point. I will be the index before this starting point. So we will always have to decrement our starting point or starting index. Here will be the loop. J will be equals to left, starting from our starting point. Less than right, of course, which is the ending point. J gets incremented. Okay, here's our base loop. We will have to put in some condition checks for the swap. If the element at j is less than or equal to pivot, perform a swap. Oh, before performing a swap, we will have to increment I. I almost forgot. Increment I, use a temporary variable to store. Okay, I will keep this. J will equal to array I. Array of I will be temporary. Okay. So now our swapping is done. And don't forget, guys, here we will have to put our pivot at its correct position at the end of our loop. I will get incremented, and the element at I is going to be the element at the right index. Oh, before that, we will have to use a temporary variable. Okay. Oh, sorry. It will be temporary, and we will return the index I. Okay. Now our function and methods are looking quite good. Let's test it out. Okay, here will be our test array. I will call the sorting method on our test array. Oh, sorry. Left will be 0, as all arrays starts with the index 0. Test. Right will be the end. Here we go, and we will print our array out. Okay, now let's run the code to see if it works. Oh wait, sorry, I used the wrong variable. Okay, there we go. So here's one. I have 3 2s. 1, 2, 3, and 3, 4, 5. 3, 4, 5. Keep in mind, guys, quicksort is not stable, meaning that these repeated numbers do not remain the same as their order. For example, these two have to come first because it is the first of all these duplicated 2s, but in this case, this wouldn't be the first coming 2, which is this one. This wouldn't be this one. And the order of these elements could have been changed during our swapping processes, during our sorting processes. So keep in mind about that. So this will be it for today, guys. Hope you liked this video. Hope this was informative. And if you want to see more content, and if you'd like to support me, like and subscribe, and make sure you give me some ideas on how to improve my videos since I'm really starting this. And thank you all for watching.